Hi, my name is Kieran Tolan. This presentation is on applying multi-agent reinforcement learning in security operations centers. I chose this topic because I work in cybersecurity and deal with the modern challenges posed by AI and machine learning to SOCs on a daily basis. Modern security operations centers face a number of challenges. Firstly, SOCs face tens of thousands of alerts daily, far beyond what human analysts can realistically manage. This constant overload makes it difficult to prioritize and respond quickly, increasing the risk of delayed threat detection. When it comes to SIM, EDR, DLP, and firewalls, each tool is effective in its own task but usually works independently. Without seamless integration, valuable insights remain trapped within individual systems, limiting visibility and slowing coordinated responses. Studies show that nearly half of all alerts are false positives. This wastes analyst time, adds noise to investigation, and delays genuine threat response. Analysts must manually investigate and escalate alerts, many of which are repetitive or of low value. Over time, this leads to alert fatigue, burnout, and reduced accuracy in detecting real threats. Current SOC operations rely on static playbooks and delayed integrations. This lack of real-time coordination means threats can spread before containment actions are executed. As SOCs grow in complexity, AI agents are emerging as essential to reduce manual effort and scale analyst capacity. AI cuts through alert noise, learns from historical context, and surfaces only what matters. This combats fatigue and accelerates response. Agents automate log collection and correlation across SIM, EDR, cloud, and identity systems. They don't just gather data, they build a narrative of attacker behavior for faster, more consistent decisions. Unlike Copilot's AI agent can initiate hunts, they establish baselines, detect anomalies, and refine models over time to catch threats early. Adaptive response workflows moves beyond static playbooks. Agents adjust in real time, learning from what worked and failed, creating continuous feedback loops for faster containment. Mapping to MITRE ATT&CK framework automates classification of observed behavior into attack techniques, which provides structured, threat-informed defense without analyst overhead. When it comes to documentation and reporting, AI auto-generates timelines, summaries, and compliance-ready reports with evidence and rationale included. Taken together, these use cases drive towards an autonomous SOC, delivering continuous detection, faster investigations, adaptive response, and less reliance on human bandwidth. Comparing agentic AI in a SOC to a smart traffic system can help simplify objectives and workflows. In intelligent transportation systems, traffic lights act as local controllers, adjusting signals to optimize vehicle flow. Similarly, in a SOC, tools like SIM, EDR, and DLP act as agents controlling different parts of the environment. Each makes local decisions but contributes to the overall flow of security operations. Just as vehicles are entities moving through the traffic system, threat events are signals flowing through a SOC. Some are benign, some are urgent, and the system must process them efficiently to avoid chaos. Traffic congestion happens when too many vehicles overwhelm the system. In SOCs, this is similar to alert overload. Analysts can't process events quickly enough, causing dangerous delays in response. Smart traffic systems reroute vehicles dynamically to avoid congestion. Similarly, a SOC can reroute or shape network flows or quarantine suspicious endpoints to keep them safe and operation. Now, ultimately, both systems share the same objective, ensuring smooth, efficient operation. For traffic, it means getting vehicles to their destination quickly and safely. For SOCs, it means minimizing detection delays, reducing analyst fatigue, and maximizing defense effectiveness. So why use multi-agent reinforcement learning in a SOC? Current SOC automation often relies on predefined rules, playbooks, or scripts. While these are useful, They are rigid and don't handle unexpected or novel attacks well. For example, a new type of malware might bypass static detection rules until analysts update them. Cyber threats evolve continuously. Attackers change tactics, techniques, and procedures. Static automation doesn't adapt in real time, and SOCs need adaptive systems that learn and evolve and don't just replay old responses. In multi-agent reinforcement learning, each SOC tool, SIM, EDR, DLP, firewall, can be modeled as an agent. Each agent makes local decisions but contributes to a shared global security objective. This turns siloed tools into a collaborative defense system. Just as traffic lights share data to avoid congestion, SOC agents share threat state information. For example, if the endpoint detection response system detects ransomware, it informs the firewall to block related IPs while the SIM updates its correlation rules. Coordination avoids bottlenecks, speeds response, and reduces duplicate or conflicting actions. This draws on the analogy of smart traffic system. Lights adapt in real time to coordinate traffic systems, reducing jams. Similarly, SOC agents can dynamically adapt to threats in real time, rerouting traffic, quarantining endpoints, or tightening policies based on an evolving environment. So what exactly is multi-agent reinforcement learning? Multi-agent reinforcement learning builds on the foundation of reinforcement learning. In reinforcement learning, a single agent learns how to make decisions by interacting with its environment. Multi-agent reinforcement learning extends this by introducing multiple agents, which acts more complexly but allows for collaborative intelligence. In multi-agent reinforcement learning, each agent not only observes the acts in the environment, but also needs to account for the actions of other agents. In cybersecurity, this could be SIM, EDR, firewall, and DLP tools, all acting as agents that share context and adapt their behavior. The system isn't just about individual wins for each agent, it's about maximizing overall system performance. In a SOC, this might mean faster detection, fewer false positive, or minimized impact from attacks. The reward is tied to the efficiency and effectiveness of the defense. Finally, multi-agent reinforcement learning can be modeled in cooperative, competitive, or mixed environments. For SOCs, this is primarily cooperative. Tools work together to improve defense. The system architecture of a multi-agent SOC consists of one, SOC tools that act as agents. Each tool is represented as an intelligent agent within the system. Instead of working in isolation, tools learn to cooperate and optimize their actions. For example, if the EDR detects suspicious activity, it shares it with the firewall agent to proactively block connections. Two, a central repository where agents log their observations and alerts. This ensures all agents have a common understanding of the current threat landscape and prevents duplicate investigations and enables correlations across tools. Three, the coordination layer is the brain of the system that manages how agents interact and coordinate. It uses multi-agent reinforcement learning algorithms to decide which responses are optimal for a particular event. Four, the reward function defines what success looks like. This may be faster detection, fewer false positives, reduced dwell time, or minimized business disruption. Agents learn policies that align with these goals. After every incident, results are fed back to the system to improve future performance. Over time, the system becomes more effective as it learns from real-world attacks. This allows the SOC to continuously adapt to new tactics, techniques, and procedures. The benefits of a multi-agent SOC are by enabling SOC tools to coordinate in real time, threats can be contained more quickly. Instead of waiting for analysts to manually trigger response actions, like blocking IPs or quarantining endpoints, this happens automatically and instantly. SOC analysts today face alert fatigue from thousands of notifications. With multi-agent reinforcement learning, many repetitive triage tasks are automated, freeing analysts to focus on higher-level investigations and threat hunting. This reduces burnout and improves efficiency. It offers real-time adaptive defense, unlike static playbooks. Agents continuously adapt to the evolving threat landscape. They can reroute traffic, tighten firewall rules, or tune detection thresholds on the fly, making defense more resilient against novel attacks. Lack of coordination is the biggest weakness in today's siloed SOCs. Multi-agent reinforcement learning incorporates collaboration. EDR, SIM, DLP, and firewall agents share threat intelligence instantly and act in sync. This avoids duplication and conflicting responses. By learning from their shared experience, agents can filter out low-value alerts. This reduces noise in the SOC, allowing analysts to focus on real, high-priority incidents. Ultimately, this leads to a more effective, quieter SOC environment. So what does the SOC of the future look like with multi-agent reinforcement learning? The next logical step is tying multi-agent reinforcement learning into XDR and SOAR platforms. These platforms already centralize detection and response, and multi-agent reinforcement learning could enhance them with adaptive decision-making and coordination across tools. A key challenge with AI in SOCs is trust. If multi-agent reinforcement learning decides to quarantine a server or block critical traffic, analysts and business leaders need to understand why. Incorporating explainable AI would provide reasoning behind each action, ensuring accountability and confidence in automation. In the future, SOCs may evolve into self-healing ecosystems. Multi-agent reinforcement learning could enable networks that automatically isolate threats, reconfigure themselves, and restore services without manual intervention. This reduces downtime and human workload during large-scale attacks. Today's SOCs operate in silos. Federated learning allows models to learn from multiple organizations' threat data without sharing sensitive raw logs. This means SOC agents could adapt to global threat patterns while preserving privacy. In summary, modern SOCs struggle with overwhelming alert volumes, a shortage of skilled analysts, and siloed tools that don't work together effectively. This creates delays in detection and response, leaving organizations exposed to fast-moving threats. Multi-agent reinforcement learning changes the game by enabling SOC tools to collaborate. Instead of static rules, tools adapt dynamically, learning from both the environment and each other to optimize threat response. The traffic light analogy is key. Just as smart traffic systems reduce congestion by working together, SOC agents can minimize alert bottlenecks and optimize defense flows. This makes security infrastructure proactive and coordinated rather than reactive and siloed. Looking ahead, SOCs could become more autonomous, multi-agent reinforcement learning agents driving continuous improvement. This points towards self-healing networks capable of detecting, containing, and remediating threats with minimal human intervention. Analysts would focus on strategy and oversight, while the system handles routine adaptive defense.